Okay, this is where we left off class period last time. We talked about this graph. Well, let me go back one slide. We talked a little bit about the idea of graphs being connected versus disconnected. So a graph is connected if you can start at one vertice and following along edges of the graph, you can get anywhere else. We talked about edges being sort of like if you were talking about a sidewalk between somewhere, a road between somewhere, you didn't have to actually get off the road and use a Jeep or whatever to do that kind of idea, okay? So we had this graph and we decided that it was disconnected. The piece that we had not decided yet is where it talked about how many components it has. So components are the pieces that are connected. So maybe the whole graph is not connected, but there's portions of the graph that are. So for instance, this little triangle over here, these three vertices, they're all connected. So that little portion of the graph is connected, right? I can get all between those three pieces right there. So I have this piece that's connected. What else do you have that's a connected piece of this graph? So I did one in yellow. What else? Okay, so all this sort of string of stuff across here, right? So those across the top, and they connect to these pieces down below. So that's another piece. So this is piece number 2, right? So my first piece was connected in yellow. And then I actually have a third piece on this one, don't I? I have this piece right here that isn't connected to anything else, but it's, by itself there in the middle. So this would be a third component of my graph. So how many components do I have? I have 3 components. I don't really need colors for this. I just used them to highlight for you for sake of argument. But we'll get to the point where we have colors later, I promise. Okay, any questions on the connected idea? Connected versus disconnected? This one's disconnected with 3 components. If the graph were connected, how many components would it have? It'd have 1. Because the whole idea of being a component is that it's the connected portions. And if you have a connected graph completely, then you only have 1 portion that has that connected ability, because you can get from one point to every other point you'd need to. Okay, sum of the degrees theorem. Now we talked a little bit about summing up degrees last time, and we did an example. And this example, or this description, actually tells you a really nice property about the degrees and summing them up. So it says, if in any graph, the sum of the degrees of the vertices equals twice the number of edges. Now, inherent in this definition, or this description, or whatever, has this sort of embedded idea of the degrees of the vertice. Do you remember how to find the degree of a vertice? Did we talk about that last time? Some of my classes are blurring together because I'm teaching very similar content, so I can't remember if I've talked about it here or not.
How many edges are connected to an individual vertex?
Right. Did we talk about that, Glenn, or is that something you just remember? We did talk about that? Okay. We highlighted over it. Okay. So if we had a graph, well, let's just go back to the last slide that I had. We can talk about the degree of any vertice. That's right, because we did an example now I'm remembering. We can talk about this vertice in particular, what I'm drawing an arrow to, and it has a degree 3 because it has 3 edges attached to it. Everybody with me on that? So the idea in this theorem is that if we found all the vertices and found all of their degrees, and we added all those degrees together, you would end up with twice as many, twice as big of a value as if you just added up all the edges. So I think we've got an example. So we've got a graph, and this does not have a picture to go with it. I don't actually see the graph, okay? But it tells me some information about it. So it says, the example says, use the theorem that relates the sum of the degrees to the number of the edges in the graph without drawing the graph. Okay, so we're not asking you to create a graph that would do this, all right? It tells you have a graph. It has 8 vertices, right? It says it has 2 that have degree 1, 3 that have degree 2, 1 that has degree 3, and 1 that has degree 5, and 1 that has degree 6. Is that 8? 2, 5, 6, 7, 8. Yeah, that's 8 vertices, so it didn't create anything that wasn't really there. And we're supposed to find out how many edges that there are in the graph is the idea. Okay, so we actually can add up how many degrees we have. We have 8 vertices. 2 vertices have degree 1. So here's vertice 1 and here's vertice 2. They have degree 1. 3 vertices have degree 2. So that's 1, 2, and 3. 3 of them have degree 2. 1 of them has degree 3. 1 has degree 5, and 1 has degree 6. Good, I count 8 of them that I listed. So I listed them each individually because I wanted you to see that there really are 8 individual values that I'm adding together. Now, if you had seen this differently, you very well might have said something like this. Well, 2 of them have degree 1, so that's 2 times 1. And 3 of them have degree 2, so that's 3 times 2. 1 of them has degree 3, 1 has degree 5, and 1 has degree 6. This adds up to the same thing. Okay, so if you see it that way better, that's fine. You're going to get the same thing either way. But what I'm doing right here is I'm finding the sum of the degrees, right? All of this does that. So take your calculator or grab yourself and your pencil and paper or whatever, add those together, multiply and add together. What do you get? What's the sum? 22. The sum is 22. Okay. How many edges then do I have? 11, right? The sum is twice the number of edges. So there are 11 edges in this graph. So if I wanted to draw this graph and I started making drawings and I somehow ended up with 13 edges, something was wrong. I didn't make the graph that they described because I should only have 11 edges. Does this make sense? So this is a counting argument is what this is. Just a little bit of arithmetic involved. All right, what do we have next? Okay, we're going to talk about 3 different kinds of, I don't know, descriptions of, I keep wanting to use the word walk or path, but those have specific meanings. But the ways in which we can traverse the vertices, so we can go across them, so we can go around or across these different vertices. The first one's called a walk. A walk is simply a sequence of vertices linked to the next by an edge. Okay, so I have a walk if I can actually go through and I can go from this vertice to this vertice to this vertice. Obviously, I have problems with that if the graph's disconnected. I can't get to every vertice, right? We talked about that already. But also, I can't get between some vertices because they don't have edges connecting them directly. Right? So if A and B are not connected by an edge, I can't go from A to B unless I pass through step C or something like that. That's a walk. A path is a walk that uses no edges more than once. Okay, so this is the idea of what you do when you go and you run errands, whether it's across campus or across town. You tend to want to make the best use of your gas money, don't you? If you're thinking wisely, you do. You don't run over to the mall and then run over to the high school and then run back to Arby's, or McDonald's or whatever. You don't do this sort of back and forthness if you can avoid it.
Not during the week unless it's a Walmart run.
So this is the idea of a path. It's the idea of not wanting to cross yourself over, right? You're wanting to actually make the most best use of your resources, and in this case, my example was your gas. A circuit is a path that begins and ends at the same vertex. So you do circuits all the time, okay? So a circuit is actually a path, so you have to be careful about that, right? It is a path. So if you've already got traversing the same thing over and over again or something like that, it can't be a circuit, okay? But you do circuits all the time, right? So you may have left your dorm room to come to class, and then you're going to go to the cafeteria, then you're going to go back to your dorm room, or something like that, okay? So this is a circuit. A circuit is the idea of being able to go sort of in a circular pattern. But again, you can't cross the same path more than once. So if you go to the lunchroom and then you come back to my room here because you left your calculator, no circuit, okay? All right, so we're going to take a look at one. Here is a, it's going to come up here eventually. There it is. All right, so we have a following graph. Obviously, there are some things I can't do. I cannot go directly from B to C. Do you guys see that?
Yeah, true.
I mean, I don't have a path that connects them. I don't have an edge that connects them. So if I want to go from B to C, I have to go through either point D or point E at minimum to get there. Okay? All right, so what we're going to do is we're going to take a couple of examples down below, and we're going to refer to the following graph. We're going to decide whether the sequence of vertices is a walk, a path, a circuit. Can it be all three? Yes, it could. It could be all three, all right? Could it be none of them? It could. That's a possibility, right? If I actually listed this stuff below and I have something that says B arrow C, that's not a walk
Right.
because I can't get there
It's not
on a
existent.
sidewalk. It would not exist. So it would be none of them. So you could have something be all three, A, B, and C. It could be none of them. Okay, so we really have to check each one individually. All right? So here's the first deal. And you can trace along your graph. That's what I'm going to do as I work to see whether it works. So this one says I start at A, and I go to B, and then I go down here to E. First question is it a walk? Can I actually do it? Yes, this is a walk. Is it a path? Yes, path simply means that it's a walk that doesn't cross over itself. I don't repeat any of the edges again, so this is a path. Is it a circuit? No. What would I do, or what could I do to turn this into a circuit? I'd add either an arrow A at the end, or I can add an E arrow at the beginning, right? And then I would both start and stop at the same place, because that's the only difference of what's going on here. If this said A, arrow B, arrow E, and then another arrow A, I'd have a circuit. I don't right now. So this is a walk and a path only. Okay? All right. All right, let me use another color. I'll just use my yellow. All right, the next one has got a really long sequence of edges that I'm going to follow. Okay? So I'm going to start at D, and I'm going to go, I'm going to go from D to C. In fact, let me make it a little bit bolder of a pen. D to C, and then C to E, and then E to B, B to D, D to A to E, and then I go from E to C. First, is it a walk? Careful. It is a walk. A walk just means that I could actually draw what I just drew, right? I could go from step to step. All of them were connected by edges that said they were connected by edges. It is a walk. Is it a path? No. What did I do? Why is it not a path? Yeah, I crossed EC twice, right? Once in each direction. The direction's not important, okay? But I did do it in each direction, but I crossed that path more than once. So this is not a path. Is it a circuit? No. Could I have made it into a circuit? I could. If I stopped after the second D here, it would have been a circuit, right? That piece right there would have been a circuit. Agreed? That would have worked. So could I take a portion of it and turn it into a circuit? Yes. This one, that's all I have is a walk, though. Okay, make sense? Walks, paths, circuits. Now, one thing that's interesting to notice is that I couldn't take this and add an arrow D on the end and turn it into a circuit. Right? If I added arrow D, I would both start and end at the same place, but it wouldn't be a circuit. Why? Because it's not a path. A circuit is automatically a path. Okay? So if I don't have a path, I do not have a circuit. Okay? In other words, I can't have a walk and a circuit, or a circuit only. Right? I can't get only a circuit in this graph. It has to be all three, or the first two, or the first one, or none of them. You can't sort of jump to say, oh, yes, it's a circuit, but it's not a walk. We don't have that possibility. Okay? All right. A complete graph. All right, so a graph is complete when there's exactly one edge that connects every two sets of vertices. All right, so that's what this says. This is a graph in which there's exactly one edge going from each vertex to each other vertex. So let me draw you one. You've seen one actually. That would be complete. Every vertex is connected by an edge to every other vertex. We could draw one that has 4 edges. I'm sorry, 4 vertices is what I meant to say. Sorry about that. So here's my 4 vertices. The graph as I've drawn it right now, though, is not complete. What's missing? I need what, Mark?
You need like top left going top right.
Okay, so I need something like, oops, I thought I drew it. Let me try again. Like this? That'd be one of the things I need, right?
Yes. And then opposite.
And I need this one as well. And I don't want to put a dot in the middle. That's not my point. Okay, so this is the overlaid idea that we talked about last time, like the highways in, Dallas and whatever, when you're looking down from on top, it looks like they're crossing. They're not really crossing each other, so there's not a point in the middle that's crossing. But each vertex then here is connected to every other vertex. And you can check to make sure that that's correct. One real quick way to do that is to check on the degree. So let's do that real quick here. On the top left corner, we're doing the square right now. The top left corner, what is the degree of this particular point right here? It's 3. What's the degree on the top right? Bottom right? Bottom left? They all have degree 3, which makes sense because there are 4 vertices, which means that if you don't count yourself, there's 3 other vertices beside you. Everything has to have degree 3. Okay, so that's good. And of course, we still can't have graphs connected to itself or 2 lines between or anything like that, which we talked about that last time about simple graphs. So this would be a complete graph. Here's an example of one too. All right, so here we have a hexagon. And the question is, determine whether the graph is a complete graph. If not, explain why it is not complete. Okay, it is not complete. Why not? Okay, so B cannot go to F, for example, right? And there's several others, right? Give me another one just so we can talk about them. A doesn't go to E. C does not go to F. Okay. All I really need is one of them, right? As long as I have one of them not happening, then it's not complete. But there's a lot of them not happening in this one. And we could double check that too with degrees the same way that I just did a minute ago, right? What is the degree of point A? It's 3. But how many points other than A are there in this graph? 5. Well, it can't be complete then, right? A is not going to 2 different points. It's not going to, let's see, E or F or D. It's actually missing 3 of them. 1, 2, 3. No, there's 7 points, so there's 6, right? 1, 2, 3, 4, 5, 6. No, I counted wrong. No, it goes to E. Sorry, it goes to F. It's just going straight there. I was overlooking that. It doesn't go to D or to E, correct? There we go, yeah. All right, so it's missing 2 because it should have degree 5 if the graph were complete, and it doesn't. In fact, all of the points have degree 3, aren't they? Or shouldn't say, don't they? Yeah, they're all missing edges that should be connected to them if the graph were complete. All right, we're going to talk sort of in passing about subgraph, not because we're going to be asked to find it or anything, but occasionally the directions will say something about subgraph, and I need you to know what it is. So if you encounter it, you're like, oh, I haven't seen that before. I don't know what that's talking about. We don't do that. So a subgraph is simply a graph with some of the original vertices and all of the original edges between them. So for instance, I know I just said that, but just pause with me so I can show you a picture. I'll promise I'll bring the slide back. We'll do this picture's fine. If I erased these 2 edges right here between D, C, and E, if I erased all this portion of it, and all I had left was this piece right here, that piece would be a subgraph. Okay, it has the points A, B, E, and D, and it has all the original lines, all the original edges. That would be a subgraph. It'd just be a sub-portion of the graph I already have. Okay, so that's all a subgraph is. Let me come back here so you guys can write it down. Now, you see the word coloring next, and that's what I told you needed to have some highlighters or markers or something with you here today for. So a coloring is simply an assignment of a color to a vertex in such a way that the vertices joined by an edge have a different color. And in most cases, 4 colors will be what you need, and I suspect if you needed more, probably somebody next to you let you borrow the color you don't have. And then a chromatic number is simply the least number of colors you need. All right, let me show you an example of how this works. Did everybody get things written down? A couple people still writing. We're going to talk about how you actually go about coloring a graph, okay? So these steps that I've got listed are not exactly the ones that are listed in your book. I've kind of abbreviated and changed some wording around to ways that I thought made it a little bit more clear. But coloring a graph. So what you do is you choose the vertex that has the highest degree. And there may be more than one. Okay, so you have to pick one of them. It doesn't matter. Pick one with the highest or greatest degree and color it. So you decide this is going to be pink, whatever. You use that same color to color as many other vertices as you can without coloring to adjacent vertices. Now, I haven't defined what adjacent vertices are, and in fact, your book never even describes them as that, but do you know what adjacent vertices should be? What should adjacent vertices mean?
Vertices that share the same edge.
They share an edge, exactly. Adjacent means next to, right? So if I say that I live adjacent to, Joe, then that means that Joe and I live beside each other, right? Our houses are beside each other, or dorm rooms, or whatever, okay? Adjacent in the sense of a graph means that they share an edge. They're next to each other. You can get from one to the other one through one edge, okay? So you want to color as many other vertices as you can with that same color, okay? Pick a new color, you do the same thing, okay? It's next highest degree, whatever's left over, and you color as many other points as you can with the pink or the purple or the green or the whatever you picked next. And you continue this until all the vertices are colored. So there's not one right answer on these. Often there's more than one coloring display you could have picked. Now, a lot of times your answer may be isomorphic to someone else's. We encountered that description last time. But it would look different if you actually looked at it, and especially even just because you might have chosen different colors. But even aside from that, the points that you picked to be all the same color may not exactly match with someone else's, and that's perfectly okay. Okay, so a degree is in reference to a particular vertice. So it's related to edges. It's the number of edges that are connected to that vertice.
So
Okay.
if you pointed at a degree or an edge, you would technically
If
be
you're-
pointing at the same line.
If you're finding the degree, you're counting edges. For instance, take a look
Okay, so
here.
the degree is like the number of edges.
It's the number of edges at that point.
Okay.
Yeah. So like on this graph right here, now this isn't exactly the graph I had when I did the complete example. My complete graph example, what's different about this graph versus the graph I did when I had a complete graph example? There is a vertice in the middle. Okay, so I want to make sure you're aware of that. And that graph, this is actually a different graph. But what's the degree of point A? 3. And the way we find that it's 3 mark is because there are 3 vertices coming out of point A or going into point A, however you think
You
about
mean
it.
edges?
3 edges. Yes, I'm sorry. I said the wrong thing, and that further completes.
What the degree is?
The degree of vertice or vertex A is 3 because there are 3 edges attached to vertex A. What's the degree of point or vertex G? That one's 6. There are actually 6 edges that are attached to point or vertex G in the middle. Okay, you ready to color? Okay, pick your favorite color. I'm going to start with yellow. We need to pick the vertex or one of the vertex points, one of the vertices that has the highest degree. Which one has the highest degree? G. And we color it whatever color you've picked for it. Now your goal before you put that color away is to see whether or not you can color any of the other vertices. And in this particular color, you can't, because every other vertex is connected by an edge to point G. Everybody with me? Okay, which means you got to pick another color next. So I'm going to go with red. You go with whatever you want. Now, pick me another vertex of highest degree of what's remaining. A. And I actually could pick any of them, couldn't I, Jordan? Yeah, because they all have the same degree of the ones that are left, right? So if you don't pick A, no problem, all right? Now, there are 3 points that I could not color in red. Point G in the middle because it's already colored. But what else? C and B cannot be colored in red. Why not? Because they're adjacent to point A. So somebody tell me a point I could color. I could color E. And anything else I could color then? D. Now you have to be careful because I could have colored F instead of A and E, and that's a possibility, right? But the problem is that if I do that, I'm going to end up needing more colors, aren't I? My goal is to use as few colors as possible. All right, so we're going to pick another color now. I'm going to go with green. Pick me a vertex. B. If I color vertex B in green, now what? Can I color the other two? I can, because neither one is adjacent to B. Now looking at my graph, looking at my colors, looking at what I've got, what is my chromatic number? It is 3. What is chromatic number again? What is it? It's how many colors I used. How many colors I had to use. Because I could have used more, right? But it's the least number of colors I had to use. There was no way to do this in fewer than 3. So the chromatic number is 3. Are we all good with that? Okay. I want to do one example problem of how graph theory is used to solve problems. And there's you're going to do a few different examples in your book, but this is one example. At a party, there were 4 males and 5 females. During the party, each male danced with each female, and no female or male pair danced together. In keeping with everything you know that you shouldn't do, right? Whatever. Drawing a graph with vertices representing the people at the party and edges showing the relationship danced with. How many edges are there in the graph? Okay, so I'm going to draw on another board. And I need vertex. No, I'm going to do the one in here. I'm going to do a vertex for every person. So how many vertices am I going to need? 9. And you want to organize this in a way that's easy for you to work with, okay? So I probably want to put all of my men on one side and all the women on the other side because it'll be easier to draw everything. Agreed? Okay, so I've got 4 men and I've got 5 women. Apparently somebody got stood up. And I'm supposed to connect, in fact, I'll label them just to make sure we're all on the same page here. These are my males, and these are my females. And so the part in parentheses, and this is straight out of your book, I didn't actually make it up, but the part in the parentheses basically tells you that none of the females get connected together and none of the males get connected together because the relationship between them is danced with. And it says no female pairs or male pairs dance together. Okay? So I'm going to take my male, my first male, and I'm going to draw a line from him to every female part on the right. So how many dances did this male have? 5. He danced 5 different dances, right?
The question is if you have a good time or not.
I don't know.
Leaving the other, if you're stranded in which one of these females he has feelings for.
That's true. Lots of confusing things, problem. Yeah. All right, let's try male number 2 because he has the same issue going on, right? Male number 2, he gets to dance with each female as well. Isn't this a wonderful graph? It's easier to draw on the iPad than it is even on the board, actually. Male number 3. He gets to dance with each female. And male number 4 as well.
That's a party.
That is a party. Now, I don't remember if we're going to get to this or not in your book, if they'd ever define it, but this is actually something that's called a bigraph from graph theory, because if you actually severed, you could actually isolate the males from the females, and there's nothing connecting all the males, and there's nothing connecting all the females, which is the definition of a bigraph. But this is the picture we have for this description. Okay, and you guys could create this, yes? You can do this same kind of picture. There's one of the classic problems in combinatorics, which is another branch of mathematics, is the handshake problem. So in other words, if everybody in this room shook the hand of every other person in this room, how many total handshakes would there be? Okay, you can do this with with graph theory as well. So you have a similar problem to that, but there's not as many people involved, so you don't have as many lines. Okay, so let's go back to this particular problem, though. The question asked is, how many edges are there? In other words, how many individual pairs of dancing occurred? That would be the correlation in this problem. How many are there, or how could you find them?
20.
There are 20. How did you get 20, Damon? Whoops.
4 times 5.
Right, there are 4 men and there are 5 women. And every vertex over here has degree 5, which we established as we went along, right? So if I add up all of these over here, this actually relates back to my idea of my sums over here. This is 20. If I added these up all over here, they're all 4. Okay, that didn't work out right. Let's try it again. And this is 4, and there's 20 over here. So the sum of all my vertices are 20 plus 20 is 40, which means there's half as many edges. There are 20 edges. So whether you're thinking in terms of that sums of degrees formula, or whether you're just thinking, or whether you just count, any of those, you can do any of the above. There are 20 edges, which is what you were asked to find. Any questions? All right.